Hi everyone, I'm Shen Yuan again. So in the first part, we'll define the loss invariant for Legendre knot in a context-free manifold. And in the second talk, I will explain the naturality of the loss invariance under positive context surgeries and its application. Okay, so the first part is just a recap, so I will not repeat that, but I do want to mention in the first talk, I only defined the certain bending number and rotation numbers for knots in R3s using the from projections, but in general, you can define that for other Legendre knot in other context-free manifold. So as we have seen, it's really hard to distinguish two Legendre knots. So that means that if you have two Legendre knots that are smoothly isotopic, how can we tell if those two are Legendre isotopic or not? So one way to tell that is using the classical invariants, those TBN rotations. But what if those two Legendre knots have the same TBN rotations? And we give a special name to those kind of knots who do have two Legendre representative have same TBN rotations, but are not Legendre isotopic. And we call those knots Legendre non-simple. So to find the Legendre non-simple knot, we need a better invariant for Legendre knot. So that's how loss invariant come to stage. Okay. So again, the loss invariant defined by Liska, Stipcher, and Sabos are using the knot flow homologies. And after they define that, also Stipchers proved the naturality result of the loss invariant under contact +1 surgery. And use that, they show a family of twisted knot is Legendre non-simple. So here is a statement of theorem. So let L and S be two Legendre knot in Y of cases. Then if you do +1 contact surgery on S, we know that it will maps from it will give rise to a map from the original context-free manifold to another context-free manifold. And smoothly this the map induced by the coordinates will provide a map from the knot floors of -YL to the knot floor of -Y +1 contact surgery on S, and together with the induced knot L of S. And the theorem states that these maps will map the loss invariant to the loss invariant. Okay. So what I did is I just extend their result by changing the +1 contact surgery to +N contact surgery. And the same statement will follow the maps on the knot floors induced by the coordinate map will map the loss invariant to the loss invariant. Okay. Here are the ideas of the proofs, maybe just for specials. So the idea is to first prove the naturality result of the loss invariant under the capping off coordinate of the open book. It's very similar to the Baldwin's proof. So Baldwin shows that the contact invariant is natural under the capping off coordinate. Then we use the correspondence between the +N contact surgery coordinates and the capping off coordinates by Liska and Stipchers, and we can conclude the theorem. Basically, their theorem says the +N contact surgery coordinate is the same thing as a capping off coordinates by viewing its upside down. Okay. So next, the theorem 3 by Stipchers is a theorem about the Legendre non-simple knot. So they found those family of twist knot ENs, so they are Legendre non-simples, and they'll have that many Lagrangian different representative with the same TB and same rotations. And this picture is a smooth picture of those knot ENs, and it's -n-1 twists. That means that in the bottom there are total n+1 left-hand twists. So using this theorem series and the +2 naturality result of the loss invariant, I can conclude the following result. So this knot, which in convex notation is -2 and -1, -n and 2, have the same number of Lagrangian representatives with the same TB rotations, but not pairwise Lagrangian isotopic. You can see that these two pictures are only differ by adding that many right-hand twists. Oh, sorry. In this green circle. Okay. And here are two examples for n equal to 5. So when n equal to 5, all the pictures shows these two Lagrangian knot have different loss invariant. So those two are not Lagrangian isotopic. And I will show the same similar things. I will show these two Lagrangian knot also have different loss invariant. So they are Lagrangian non-isotopic. Okay, so the idea, as you may guess from the previous pictures, is just construct the new one from the old, and to say something like if the old one have two different loss invariants and the new one have two different loss invariants. Okay. So how to construct it? So we first consider triple L sigma n b, where L is a Lagrangian knot, sigma n is a collection of oriented arc of the Lagrangian knot L, and B is a standard double ball. Okay, and we say these triples is a compatible triple if the following hold: if the standard double ball only intersect the Lagrangian knot at those Lagrangian arc. Moreover, inside the double ball, the from projection of those EIs are horizontal parallel and have the same orientations. And in the left corner, so this is the examples of showing these compatible triples. So in this situation, it only have two arcs, so it's sigma 2, and they are like and this dotted line indicates the double balls, and those red and blue arcs are part of Lagrangian knot. And I don't know what happens outside, and I only care like the locally. Okay, so given this a compatible pair, I can construct new Lagrangian knot L sigma from L just by adding a full non-zigzag positive twist to all of those parallel oriented arc. So this right bottom pictures is showing this L of sigma. So if there's more arc, you just add a full twist. And the theorem says, suppose you have two pair of compatible triples, and if we assume L and L prime are smoothly isotopic, moreover, there exists an isotopy of L and L prime that sends like each individual arcs EI to EI prime, and the ball B contact morphic to the double ball B prime. Then we can conclude that the two new Lagrangian knot L sigma and L prime sigma prime are smoothly isotopic. Moreover, if L and L prime have different loss invariant, then L sigma and L prime sigma prime also have different loss invariant. So to prove this theorem, I need the following lemma. So this is lemma 6. So lemma 6 says if you consider those parallel oriented arcs and you do a +2 contact surgery on this, maybe I'll call it meridian or not, then the resulting one is this parallel push off of the negative stabilized arc. Okay, and the same for the other orientation. So smoothly, we're just this +2 contact surgery is smoothly just a +1 surgery on the unknown on strength. So in that smooth case, the result should just adding a full negative twist, and you can see that this is adding a full negative twist, but it's like a it's a stabilization. Okay, and to prove that, I only need to show you like the case when there's only one arc, because the other arcs are just the Lagrangian push off of that. And here's the proof. And using the contact surgery diagrams and maybe contact handles. Okay. So then I can prove the theorem 5. So in the theorem 5, you should think the red part of the first pictures is L of sigma or L prime of sigma prime. Then I do this. So L sigma is adding full positive twist on the arcs on L. And after I do this +2 contact surgeries on it becomes adding a negative twist, then adding a positive twist. So those twists will cancel out even in the Lagrangian situations. By cancel out, I mean the result one will becomes splitted stabilization of the original EI. Okay, so that means your +2 contact surgery will send your L of sigma to the original L with a negative stabilization. Okay, then by the naturality theorem, it says it will send the loss invariant of L sigma to the loss invariant of L with negative stabilizations. Moreover, by the theorem from Liska, Ozawa, Stipchen-Sabo, the negative stabilizations won't change the loss invariant. So it's equal to the loss invariant of the original node L. And you do the similar things for the L prime sigma prime. You map the loss invariant of L prime sigma prime to the loss invariant of L prime. Because loss invariant of L and L prime are different, the loss invariant of L sigma and L prime sigma primes are different. That proves the theorem 5. Okay, then use that to prove the theorem 4. So this is a Lagrangian description of the those twist knots ENs, and so it satisfies K plus L minus 1 equal to N. And two Lagrangian, if you have two different representative of these ENs, those two diagrams have the different loss invariant if K is bigger than L and K is not equal to K prime. Okay, so basically if the diagram looks different, they are different. So it's just like, just like in this picture. So in this parts, K is equal to 3 and L is also equal to 3. And in this one, K is equal to 5, L equal to 1. So those two have different loss invariants and they are Lagrangian non-simple. Then I found those double boards which indicated in greens and those two arcs where I put the orientations on. Then use the theorem 5, right? I can add a twist to those. And the theorem 5 says if the starting two are Lagrangian like have different loss invariants, then after I add twist, the result two also need to have different loss invariant. So that proved the theorem 4. So in theorem 4, I basically just add a twist in this first crossing part. Okay. So now you may think, can I do more? Can I just add like twists in other strands? So this is just smooth picture of the previous discussion, right? So I just add twists in this green part, it becomes 2m plus 1. Okay. So back to that. So we don't need to choose the double ball for just these two arcs. We can choose other double balls, like for example, this blue one. It also contains two arcs and they're parallel to each other's. And I can add 2 to that. And the result one will also have different loss invariant by theorem 5. And if you apply that to the blue circles, you will give a family of double twist knot. Moreover, what if I do it on the red arc? You can see in the red circle. In the red circle, there's a 3 parallel arcs, and if I add a 4 right hand twist to all 3 of them, I will get another like family of knots, and they also have a different loss invariant by theorem 5. Okay, so moreover, like this is another examples of Lagrangian non-simple knot. So these are Lagrangian front projections for 2-3 cables and 2-3 torus knot. So the left hand side have loss invariant equal to 0, and the right hand side has non-zero loss invariant. And here you can also find this green circle indicated the green, like the double balls, and you can see that there are also parallel arcs in there, and by the theorem 5, you can add a twist to them, so you will also get like the results, the Lagrangian knot are also have different loss invariant, so there are also Lagrangian non-simples. By the way, these dotted regions means that these two Lagrangian knots only differ in this region. So they are like smoothly isotopic. You can smoothly isotopic just inside these dotted regions. So that means that smoothly isotopic from the left one to the right one will fix the other part. Especially it will fix the ball, and so it satisfies the criterion of the theorem 5. Maybe I should mention a little bit. So the theorem 5 says then to smoothly isotopic, and the isotopic sends this arc to another's, and the ball contact morphing to ball. And we can see that in these pictures, smoothly you can just do this flag move, and you just you can just move the twist from the left to right from the bottom, and you can fix this top part. So that means it's actually this smoothly isotopic will fix this ball, right? So that's automatically satisfy the criterions. So you can add a twist to them, and the result will also be Lagrangian non-simple because they have different loss invariant. Okay, so that's all I want to say. Thank you for your attention, and let me know if you have any questions. Please ask.